Well, hello there, and welcome to the physics lab.
Hey, say hi.
So suppose you are at rest in a downward dog yoga position and we're told to stand up instantaneously in under a millisecond. Is this even possible for anyone to do? Or how about when you are running and must turn right within a nanosecond? Probably not. It would be incredibly difficult to do so. To stand up from rest or turn right in motion, you would have to steadily do so. This is described as Newton's first law, that is, because objects at rest remain at rest, and a moving object traveling with the same speed and in a straight line will continue to move in a straight line unless it is altered by an external force. We will be demonstrating this law of motion by pulling the cloth off the table with objects on top of it. External net forces are applied to this cloth to move it. Theoretically, the cloth will continue to move with enough inertia. The toys, however, move slightly downward due to gravity, but for the most part remain at rest.
Physics lab, it's not all work and no play.
Hey, come. Hey.
For Newton's second law, it states that force changes Newton's first law.
In physics, this is represented by the equation of force equals mass times acceleration, where acceleration occurs when a force or forces act on a mass or object. A primary example of this is a person walking their dog. When a person is walking their dog, they would have to pull on the dog's leash occasionally by exerting a force on the leash tied around its neck. Consequently, this force will cause the dog to experience an acceleration that is equal to the force applied divided by the mass of the dog. Newton's second law can easily be used to describe the case of Tang and his tugging toy. When two forces act on the same object, the greater force will produce more acceleration than the smaller force. Therefore, when Tang and his owner both tug on the toy, this represents the two forces on the mass or object. And in this case, the object that both forces are acting on is Tang's toy. Notice how as soon as Tang lets go of his toy, the greater force of his owner produces more acceleration than the smaller force of Tang. Tang still produces some acceleration, but it is less compared to that of his owner. If Tang exerted more force on the toy, then he would have produced more acceleration on the toy than his owner. This means that the toy would have experienced acceleration, but the majority of that acceleration would be coming from Tang.
Newton's third law states that for every action, there is an equal and opposite reaction. We can see an example of this law here with the bouncing of a beach ball. The force being exerted downwards by high, along with gravity, causes the ball to accelerate towards the ground. Once the ball impacts the ground, the equal and opposite reaction, or the normal force, will compress the ball, causing it to slow down and lose downward velocity. As the ball decompresses, the elastic energy will change to kinetic energy, and along with the force of the opposing reaction, will cause the upward acceleration of the ball to be greater than the downward acceleration caused by gravity. Once this upward acceleration is greater than that of the downward acceleration, this will cause the ball to bounce upward. However, an equal and opposite reaction doesn't necessarily mean that both objects will move in the same way. As we can see here, Tang is pushing a beach ball forward. Newton's third law states that whenever Tang pushes the ball will also have an equal and opposite push on Tang. However, as we can see, the ball moves, but Tang does not. This relates to Newton's first two laws, as Tang's ability to resist acceleration or changes in motion is much higher than that of the beach ball.
Now we are testing the free fall motion, which means on the object, gravity is the only force. Here, Jordan released the two puffy alligators at the same time. No surprise they land at the same time. Now we are testing two different objects based on the Galileo theory that acceleration is independent from mass. So, it doesn't matter what's the mass of the objects, they should touch the ground at the same time. Let's see. In our test, we assume that we don't have any air resistance. Air resistance is based on the object's shape, and the air resistance can drag the object, and it can change the result. When we throw an object upward, the motion of the object can be described as the projectile motion, which is a combination of a vertical and a horizontal motion. The vertical motion of the object is affected by the force of the gravity When the object moves upwards, its velocity decreasing until it reaches the maximum height, where its velocity becomes to 0. The object starts to falling downwards. Velocity will increase until it reaches the initial velocity.